Twinkle, twinkle, little star. I imagine that hundreds of thousands of generations have wondered what they are. Here I am again in my backyard, looking at the Big Dipper. On a clear, dark night, I can see around 1,000 stars. For the longest time, it was not known whether stars like these shined by their own light or whether they were reflecting the sun's light, as all the planets, moons, comets, and asteroids do. It's only in the last couple of generations that we have finally reached a point where we know what stars are. You'll recall that Copernicus first proposed a sun-centric model for the solar system, but you'll note that the outermost celestial sphere did not go away with the Copernican model. Parallax measurements showed us that the sun was at the center of our planetary system, but no one could find any parallax in the stars. Not Tycho Brahe, not Kepler, not Galileo, not even Newton. The reason it took so long is that stars are so very far away that parallax angles are just too small for the available instruments. Remember that the moon's parallax was 1/2 of a degree, but star parallax is measured in fractions of an arc-second. In the 1830s, there was a race to see who could find the first real stellar parallax. The astronomer Frederick Bessel won. The star was 61 Cygni. Here's how it works. If you recall, the maximum baseline for parallax measurement for planets was the diameter of the Earth. For stellar parallax, we have the diameter of the Earth's orbit around the Sun. That's an increase from 8,000 miles to 186 million miles. So from one side of the Earth's orbit, say in July, we take a line to the star and map the positions of the more distant stars. 6 months later, in January, we repeat the process. This gives us the angle theta. We define stellar parallax as 1/2 this angle. This would be the angle at the star, with the Earth and the Sun marking the other two corners of the right triangle. The math is the same trigonometry we use for finding distances to the rock in my backyard and to planets in our solar system. In 1838, after thousands of measurements and calculations, he made scientific headlines by announcing that the parallax for 61 Cygni was 0.314 arc-seconds. That gives us a distance of 61 trillion miles. That's over 6 million times further from the Sun than we are, way too far to be reflecting the Sun's light. So at this point, in the middle of the 19th century, we knew that stars burned with their own light. You may have heard the term parsec. Astronomers like to use it for measuring distance to stars. Using the method described here, a parsec is the distance an object would be if its parallax was 1 arc-second. It gets the name from the first syllable of parallax and the first syllable of second. It computes to 19.2 trillion miles. As we discussed in our segment on the solar system, light travels at 186,000 miles a second. That totals 5.86 trillion miles per year. We call that 1 light year. So 1 parsec is equal to 3.262 light years. I'll use light years throughout this video book, but parsecs will come up from time to time. Let's take a look at some of the stars in our neighborhood, out to around 25 light years. That's about as far as stellar parallax measurements from ground-based telescopes can take us. Proxima Centauri is a dim red star. It is the nearest known star to the Sun. Alpha Centauri A and B form a close binary system that is separated on average by a distance slightly greater than the distance between Uranus and the Sun. Alpha Centauri A, the main star, is bright and yellowish. B is not quite as bright and has an orange tinge. Barnard's star is a dim red star. It's called a runaway star because it's approaching the Sun so rapidly that around 11,700 AD, it will be 3.8 light years from the Sun, and that will make it the closest star to our own. This motion across the sky is called proper motion. This rapid motion is easily identified using parallax techniques. Here's a look at Barnard's star photographed in 1985. Its parallax measurement indicates that its distance is 5.98 light years. In the second photograph, taken 20 years later in 2005, we see that the star has moved 200 arc seconds, and its new distance is 5.94 light years. That's 10 seconds of arc across the sky per year. Getting back to nearby stars, here's Wolf 359. It is another dim red star. In fact, it's one of the least luminous stars known. Star Trek fans might recognize Wolf 359 as the scene of a great battle between the Federation and the Borg. Lalande 21185 is another dim red star. Recent analysis indicates that it may also be accompanied by at least 2 orbiting planets, but this has not yet been confirmed. Planet hunting is a hot topic these days, and research is ongoing. This Hubble image shows a white Sirius A, the brightest star in our nighttime sky, along with its faint, white, tiny stellar companion, Sirius B. The two stars revolve around each other every 50 years. Here we have our first parallax star, 61 Cygni again. It has another claim to fame in that it was first noted to have a high proper motion as early as 1792, when it got the nickname Flying Star. To add further to its uniqueness, in 1830, 61 Cygni was determined to be a binary star system with 2 orange stars. Altair is a bright white star. A recent study revealed that Altair is not spherical, but is flattened at the poles due to a high rate of rotation. This image of Fomalhaut, surrounded by a ring of debris, was taken by Hubble. The white dot in the center of the image marks the star's location. It's a bright white star, but the region around it is black because astronomers use the advanced camera capabilities to block out the star's bright glare so that a dim planet called Fomalhaut B could be seen. The small white box at the lower right pinpoints the planet's location. These observations offer insights into our solar system's formative years, when the planets played a game of demolition derby. Vega is a bright white star and one of the most luminous stars in the Sun's neighborhood. It has been extensively studied. It was the first star to be photographed by astronomers in 1850. It was the North Pole star around 12,000 BC and will be so again around 13,700 AD. So far, we've identified Wolf 359 as one of the least luminous stars in our neighborhood, and Vega as one of the most luminous, but we haven't been explicit as to what we mean by luminous. Stars have a wide range of apparent brightness as measured here on Earth. The variation in apparent star brightness is caused by 2 things. 1, stars have different intrinsic luminosity, and 2, stars are located at different distances from us. An intrinsically faint nearby star can appear to be just as bright to us on Earth as an intrinsically luminous star further away. Luminosity is what we use to put precise measurements on the idea of brightness. It measures the total amount of electromagnetic energy emitted by a star in watts, just like a light bulb. Apparent brightness is measured in watts per square meter. Because light from stars spreads out over the surface area of a sphere, we can use the inverse square law to categorize luminosity for all the stars that have parallax distance information. Take the Sun, for example. The apparent luminosity of the Sun, as measured in my backyard, is 1400 watts per square meter. If my backyard solar cells were 100% efficient, that's how much electricity each panel would create. Unfortunately, current technology is only 15% efficient, so I'm only getting around 200 watts per panel. Plugging our distance to the Sun into the inverse square law, we calculate its total luminosity. Here you can see that the answer is a very big number. Using Einstein's famous E equals mc squared, or energy equals mass times the speed of light squared, we calculate that the Sun is fusing 600 million tons of hydrogen into helium every second, and in the process converting 4 million tons of matter into energy every second. To put this into perspective, this number is equivalent to around 4 billion hydrogen bombs exploding every second. Astronomers use a more complex set of classifications for calculating brightness called magnitudes and absolute magnitudes at 10 parsecs. But for our purposes, we'll stick with luminosity. Getting back to stars, here's Pollux, a bright orange star. In 2006, it was confirmed to have an orbiting planet. Arcturus is an even brighter orange star. In fact, it is the fourth most luminous star in the Sun's neighborhood. GJ 1214 is a dim reddish star. Observations by Hubble in 2009 discovered GJ 1214b, a water-world planet enshrouded by a thick, steamy, water-rich atmosphere. Here we see an artist's conception of the new water planet. Capella has a rich yellow color and is the third brightest star in the northern hemisphere after Arcturus and Vega. Closer examination finds that Capella is actually 4 stars organized as 2 binary systems. Castor is actually 3 sets of binary systems, with some bright yellow and some dim red stars. Since 1838, many astronomers have spent decades measuring star parallaxes. But the work is so painstaking that up until 1989, only a few hundred were measured. That's out of a total population of over 1,500 stars within 60 light years from us. In 1989, however, the European Space Agency launched a spacecraft called Parallax. It was specially designed to accurately measure parallaxes without all the interference from the Earth's atmosphere. It did so for over 118,000 stars. Parallax is accurate to within 5 to 10% for stars within 650 light years. So let's take a look at a few of these. HD 189733 is another binary system, with the primary star being a dim orange star and the secondary star being a dim red star. As we zoom into the star, you can see the Dumbbell Planetary Nebula. We'll cover these objects in the next section. Hubble has made the first detection ever of an organic molecule in the atmosphere of a Jupiter-sized planet orbiting this star. The molecule is methane. Under the right circumstances, methane can play a key role in prebiotic chemistry, the chemical reactions considered necessary to form life as we know it. Aldebaran is a very bright red star. It may have a brown dwarf companion. A brown dwarf is a star that did not have enough mass to trigger fusion, so it only produces light via conventional means. This makes it very hard to see. Mizar is a bright white star. It is famous for being the first binary star system discovered. Galileo studied it extensively. These two stars take thousands of years to revolve around each other, so they were not seen to be rotating around each other in those days. It wasn't until the early 1800s that binary stars rotating around each other were seen. This turned out to be the first real evidence that gravitational influences existed outside of our solar system. Half of all stars are binary, or larger. In the 1900s, they were key to measuring a star's mass. Once the mass of enough binary stars were calculated, it became possible to plot mass versus luminosity on a graph. Here's what they found. Instead of having any combination of mass and luminosity, we see that stars fall in a line from low mass, low luminosity to high mass, high luminosity. But it is not linear. Each time the mass is doubled, the luminosity goes up 11 times. This relationship seems to work for most stars that aren't too massive. Note that this is an empirical relationship. We don't start with an equation and plot its graph. We observe events to create the graph, and then find an equation that would have created a graph that looks like the one or fits the one we observed. Now back to stars again. Spica is a blue star and the 15th brightest star in the nighttime sky. It's a close binary system whose components orbit each other every 4 days. Mira is a very high proper motion red star that is shedding an enormous tail of material. The tail stretches a startling 13 light years across the sky. It has released enough material over the past 30,000 years to seed at least 3,000 Earth-sized planets, and it's ripping along at 291,000 miles per hour. Polaris is our current-day North Star, for it lies less than 1 degree from the North Celestial Pole. It is a double star system, with one being a supergiant. The supergiant is a classic Cepheid variable star. Cepheids are a critically important kind of star for our distance ladder. I'll talk more about them in a minute when we come to Delta Cepheid, the first Cepheid star completely analyzed. Antares is a bright red star, the 16th brightest star in the nighttime sky. The size of Antares has been calculated using its parallax and angular diameter. Its radius is 822 times larger than our Sun's. We have now visited a number of stars from our local neighborhood. We started with the nearest stars where parallax measurement from Earth-bound telescopes were good enough. We then moved out to the further reaches of our neighborhood using Hipparchus-based parallax measurements. But now we are at a distance where parallax measurement becomes increasingly problematic, even for space telescopes like Hubble. We have around 3 million stars within parallax reach, but this is a tiny fraction of the hundreds of billions of stars in the Milky Way. If all we had was parallax, we know very little about our galaxy, and virtually nothing about the universe beyond. But the only other thing we can get from a star is its light.